Hey everybody, this is Larry. This is day 27 with Leetcode Daily Challenge. Let's get started. Hit the like button, the subscribe button, and join me on Discord. Construct binary tree from Inorder and Postorder Traversal. Yeah, so this is a pretty standard problem to get asked, so definitely practice it. The idea is try to figure out the invariant and what each prefix mean at every time. I think in order means, you know, left left, root, right. So then from that we can kind of figure out one by one, and I think one way you can do it is just by doing recursion and finding out, okay, here's an 9 from the in order and here's the post order, and post order of course is 9 in this case. You know, it does the leaps first, so from here it would go 9 and then it go 15 and 7 and so forth, right? But if you do it that way recursively, I think it gets a little bit nasty in terms of complexity if you do it right, because of the searching. So I recommend, yeah, just thinking about it that way. So yeah, cool. Yeah, so I think I will try to think about the recurrence from that, or the invariant from that. Yeah, so the first number is always going to be the left most component, and then from that we also, that should be probably the first post order, but I have to build a tree from the list. Okay, so then I guess the question is, what does this mean, right? What does this 3 mean? So post order means that that the root of the node will be at the very end, right? So we could kind of almost look at it from the back of the post order thing. So that means that the 3 of the root, so then from here 3 is the root, that means that this is from the in order way, then 3 is the root, and then 9 is to the left, and then this is to the right. And if we want to kind of go from right to left on the post order, otherwise it maybe get a little bit messy, post on the right for post order, then we just want to take this, the 3 elements, so we want to take 3 elements on the post order and go to the right, and then recursively do that as well. So I think that's what I'm going to play around with. Yeah, so that's what I'm going to play around with. I might have to figure it out. It's been a while since I did this problem, to be honest, like this sort of problem. So yeah. Okay. Okay. So let's just say index is equal to n minus 1, where n is equal to the length of the post order. Probably still want to do recursively. So now what I'm thinking now is just trying to think about how to do it recursively in a good performance kind of way. Because now we look for 3, we have to do a linear search to find 3. 20, we have to do a linear search even in the subtree to find 20, right? So I think another way to do it maybe just to have a lookup mapping to this, so that we can cut down the running time in the cost of space. So okay, so I think I'm going to do that for the Inorder Lookup. I'll call it that is equal to a hash table of 4. Yeah, for index x in enumerate Inorder Lookup. Let's do yeah, Inorder Lookup of x is equal to index, right? Of course I reused index, so that's terrible. Let's just call this post order index, so that we could kind of just process from the back one by one to get to recursively get the root node, right? Yeah. Okay, so given these 2, now let's figure it out. Okay, so now we want to, let's start by parsing from, maybe the post order index is a little bit silly. No, that should be okay. So now we want to start by having a recursive function. We have to get a tree. Okay, we'll have to merge some stuff together, but we want to parse, let's say, left and right of the in order, and this allows us to kind of split between the left and the right as we go, because post order there's an because we just keep track of the index, we just go from right to left to get the node every time, or the root node every time. And here we want to divide left and right, so then these become segments, right? So yeah. So basically, if left is equal to right, that means that they're the same index. Let's return a new tree node of I guess just in order of left, because they're the same. And then now we're given a sub-segment to handle, and then we have to try to get the what are we trying to get? Oh yeah, one of these. Let's say we're looking at this sub-segment. One of these three sub-segments will be on the post order pop. So we could do that. Let's non-local post order index, and yeah, let's fetch that. So we have to let's just call it yu to find. Let's also double check with. Okay, I just am double checking that the duplicates cannot exist. Otherwise, maybe a little bit harder. Well, actually, it's a lot harder. So yeah, it's equal to in post order index, and then we decrement it to go to 0 or towards 0. Sorry. And then here we're able to find the index of the root, right? So this is the node of the root node. Root is equal to tree node of the in-order value of the in-order lookup. So basically now we're looking up what this value to find is, and then create a tree node from that, right? But actually, before that, let's go root index is equal to this index, right? And then the reason why we now need this is now we want to, because we're going backwards, we want to count. Now we found this middle one, for example. Now we want to find the right and the left. Because this is post order, we're going to do the right first, right? So that's yeah. So then root dot right is equal to just recursively parse. So now it is the root index plus 1 to the right node inclusive, right? So let's do that. What do we say? Oh, and I think we need another thingy, but root index plus 1, right? And we need just to do if left is greater than right, return none. And then after that, root dot left is equal to parse of left to root index minus 1, right? And I think that's all you need. So now we can just return parse from 0 to n minus 1. And I hope I don't have any off by ones, but otherwise let's kind of take a look. Okay, key error 3. Did I not put that in? Because this should be in, right? In order. Oh, whoops. That's just a typo. That's fine. We were just looking the map to enumerate it, so that's silly. Well, still not correct, but oh, we forgot to return the root in this case. A little bit of a silliness, but yeah. So that looks good. Let's just try one node case, and in theory, I would test a lot more cases, and if you have time and practice, I would add more. But I just wanted to, I'm a little bit lazy, I guess is my point. I used to do it on stream, so let's submit it and then get the test cases that way. Ooh, wrong answer. Oh no. What does this visualization button do? 1, 2. Oh wow, that created a lot of stuff. So I definitely have some issues here. Maybe with an off by, maybe with some an edge case. Actually, that's what it feels like to me. So let's take a look. So I have this whole mess. How did this happen? Let me see if I did any typo-y stuff. But what is this visual? Let's visualize this. How did this happen? So the root is 3. That's good. And then the 4 on the right, and then 4 on the left. That's odd, right? So let's maybe print out root dot or yu to find and root index. Yeah, 3 is 2, that's right. 4 is 3. So we do the recursive enough correct number of times. So maybe I'm just having a typo somewhere. So let's see. Or this is how did this happen? Dong dong dong. How does this go again? So left is equal to pos of. It should just return none, right? Let's see. Left, right. Yeah, left, right is 0 and what? For the 4. Am I reading this right? So for the 3, it looks at index 2, it goes from 0 to 3 inclusive, right? And then now, when it gets to the 4, it sees as in 3 index, but the left, right is, so did I just, did I swap them? That doesn't seem to make sense. Where's the right answer? Did I mix it up? No, this is should be right. It goes to the 4 and 4, but why is the left and the right for the 4 so weird? Because this should be, it should be oh, I see, because in this case I don't decrement, that's why. Yeah, okay, I see. That is actually a subtle bug, maybe. But in this case I need to decrement so that I don't go again. Okay. Wow, that is subtle, because it was returning early that I had to pause again. Okay, that was just a silly mistake on keeping the global state, and that's why in general you don't want to do that, but well, here I am. Cool. Yeah, so that's how I would solve it. Mine is a really subtle bug. I think that's just mostly okay. Yeah. So what is the complexity? Complexity is that for each node, we're going to, well, we only create each node once, and each left and the right could only add one node. So this is linear time and O of n time and O of n space, because we have lookup tables, and also we have to create a node for each item, right? So yeah, and that's the output. So it's going to be the low bound. Yeah, that's all I have for this problem. Like I said, it's a standard problem, so definitely practice it. Let me know what you think. Hit the like button, hit the subscribe button, and I will see y'all later. Bye bye.